Hello and welcome to today's electronic design webinar entitled Long-Term Storage and the Impact on Part Solderability, sponsored by Rochester Electronics. I'm Bill Wong, editor and senior content director for electronic design with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit it to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the electronic design website within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our speakers for today's discussion. Dan Dice is the Vice President of Design Technology at Rochester Electronics. Neil He is a Senior Quality Assurance Engineer at Rochester Electronics. So welcome, Neil and Dan. Dan, the floor is yours.
Thank you, Bill. I appreciate it. And welcome to our webinar today on the long-term storage and impact on part solderability. And first of all, I want to thank you all for coming. And our contact information there of both Neil and myself is on the page in front of you. And also I want to reference everybody to all of the material that we've got posted on the webinar login link, the page that you were on, that gives you all kinds of background material for this webinar as well. And this is the third paper that we published, and want to really, this is the final paper of our long study that we've been doing in 3 parts, which focus on long-term storage, component solderability, mechanical integrity, and so forth, really getting to the bottom of long-term storage effects and whether or not date code makes sense. So with that, today's agenda that we want to cover is really start out with trends, because the trends are going to lead to a discussion about why we think long-term storage in fully authorized product is going to start being more and more often something that happens. Options for extending component availability, overview of traditional solderability test methods. That's where I'll pass it to Neil, and the results of our studies, finishing off with summary and Q&A. And please, as we start covering some material, please ask those questions. If we don't get to them here on the webinar, we'll get to you after the webinar is done. So please ask away. So I want to talk a little bit about market share and why that, and life cycle requirements by industry and how that will matter. If you look at the traditional data that comes out of the Semiconductor Industry Association, kind of the World Semiconductor Trade group there, you can see that the semiconductor market is dominated by data center silicon, portables, phones, automotive, and then the rest become consumer, industrial, and government spending. That doesn't necessarily correlate to industries that need long-term solutions. And most of the demand aren't for long-term solutions. So if you fall back to automotive and industrial as good examples, those are all going to be greater than 7 years, more like 15, 20, 30, 50. We see all kinds of demand there, but all the other high volume applications are shorter demand. So as an example, I'm going to cover 3 different market segments just as an example that kind of drive the long-term demand, and really automotive. If you bought a car in the last 2, 3, 5 years, last year, you just see how much electronics are getting put in there. That's not a short-term market. Right now, everybody who is trying to come out with anything with a car is trying to guarantee 15-year availability from the first introduction of a product. That's the guys on the right in that pie chart. If you well, let's kind of go back to that here. Sorry about that. If you look at the pie chart there on the right, where it's the worldwide automotive semiconductor market, you see the semiconductor companies and calling on the automotive market. They're really driven for 15-year availability and at minimum on a product, but it really ends up going further than that. So automotive is a key driver for long-term solutions. If you look at commercial avionics, that is a booming market. The backlog on this thing is actually way the heck out, and their demand is a very long time per system as well. And so these guys are going to be driving long-term storage, long-term availability always. And the last market I'll mention, of course, is military, and that's included in the government pie chart there. So a very small percentage of the overall semiconductor market. But you see awarded systems here, just Patriot, HIMARS, Chinook, Eurofighter, different systems being awarded still in the billions of dollars that are going to demand long-term life for sure. So we got these markets that are driving long-term, and we also have some trends happening. Parts are becoming obsolete at a faster and faster rate, and you've got a big thing that we're seeing going to drive storage of product is that the major offshore and assembly people are moving away from any package that requires trim and form tooling. So what does that mean? That means PLCCs already going away. Quads will be going away. And it's going to become fewer and fewer and fewer suppliers who can do or will do products, packages that need trim and form tooling. So what does that mean? If you've got a bunch of package assembly types that are going away last time buy, that means the lead frame suppliers are also getting fewer and fewer in the marketplace. And the trim and form manufacturers, the vendors of the equipment who actually do that, are becoming fewer and fewer. One of the options for people is, and I'll cover that in the next slide, is that you buy and store. But the buy and store method, you're going to be concerned about long-term storage. And that's what the data my friend Neil here will be talking about. If you store it and you're fully authorized, you're going to end up with a solid solution. We also see suppliers consolidating product lines. This has been a downturn in the semiconductor industry. What do they do in a downturn? Well, they trim product lines. That's kind of a very natural thing to do in a downturn, is you refocus, you figure out what's working and what isn't, and then you bring in the last time buys and you get out of things that aren't. So that's another trend or a challenge or a risk. Simply trying to manage an OSAT supply chain, that's not real manufacturing, and that's just making phone calls and hoping everyone in that supply chain is still going to be around doing what they're doing, even as the volumes get lower. It's still going to be a challenge to find your lead frame supplier. You're going to find that people aren't going to want to do trim and form tooling, and that's just really not that's not real manufacturing. The latest CHIPS Act investments are primarily for leading edge technologies, not going to help where package assembly types are going away, where older foundry technologies are going away. You see that there's been all kinds of obsolescence of stateside older technologies. CHIPS Act really isn't helping that. And so we're going to get more and more demand for stored product. There's been a strong growth in fabless IC revenue. A lot of famous companies are fabless, in fact. Well, that means they don't dictate fab process availability. So half of the companies in the top 10 are fabless. They don't drive the process anymore. The likes of TSMC and Samsung and Global Foundries really do that. So options, not really all that good, but there are some. You can do a last time buy and store the product in-house. That's absolutely, you're able to do that, and but it's cash out right now. You can purchase long-term components from an authorized distributor. That's good, but there's likely to be a limited supply, and you need to ensure components are new, unused, authorized suppliers only. And the last is to work with a licensed manufacturer who's investing in their own manufacturing and authorized to continue component supply. I think we can help with that, but let's get into the meat of the presentation. And with that, I turn it over to Neil.
Okay, thank you very much, Dan. So now that we have that understanding of the market forces driving interest in long-term stored products, I want to cover what we have previously found in Rochester Electronics studies on long-term storage, on long-term storage's effects on product, and specifically what we covered in our last paper. So in this last paper, we looked at a similar distribution of parts that we have in the current paper, and we looked at what are going to be the factors that determine actual function for you, our customers. So we looked at the internal mechanical integrity of these products after long-term storage. We looked at whether they'll adhere to a board, and we looked at whether they will function electrically. So our studies found that, and as you can see from the photos, nice solder fillets through both optical inspection and X-ray, and decapsulation showed that the die itself remained intact after periods of storage ranging up to 12 or 15 years. And again, on different package types, in this study we looked at PLCC, TSSOP, and QFN package types, as well as PDIPs. And so here you can see for the variety of different types of products through both X-ray of the package itself, again, another image, closer magnification of a decapsulated part, looking at the die, specifically also looking at the wire bonds, both the ball bond on the die as well as the wedge bond on the lead frame. Both of those look intact. And through cross-sectioning as well, we were able to see that the internals also look good from a cross-sectional view, with ball bonds well adhered, the die-attached fillet looking good, and all those mechanical factors that lead to reliability still looking great 4 to 14 years of age. So that brings us into today's topic, which is the third paper and the third study that Rochester Electronics has embarked upon and recently published. So after examining these factors of whether the product still performs in what we believe to be the most functional fit, what we wanted to look at was to compare now and go on a deeper dive into the solderability testing to see whether those function and the solderability test methods outlined by the industry would be consistent. So to do this, we looked at the several different types of methods used for solderability testing. So there are two main types of tests, one being a dip and look test, primarily used for leaded packages, particularly for through-hole packages, but also used for some leadless packages. And this test method uses a molten solder bath, so molten solder with a robotic dipping arm that plunges the device at a controlled rate of immersion and immersion into both flux first and then into the molten solder. And then this may be repeated several times for the different devices that require rotation, and then the device is inspected to see whether that solder coverage is robust. So this is the most commonly used test in industry, which may be because that the equipment is widely available, it's semi-automated, and so it's relatively easy to implement across different types of products, across different types of packages, and across different operators, different staffing. However, one thing that comes immediately to mind when we're discussing surface mount packages is that this is a test that really simulates wave solder and mounting for through-hole components. It's not very analogous to the ways in which parts are mounted to boards now, which is reflow process. So the other test method, primarily outlined by the standard and also used in industry, is the surface mount process simulation test. And in this SMT simulation test, parts are placed onto a ceramic substrate and sent through reflow. So first, on this ceramic nonstick substrate, solder paste is deposited according to the solder land pattern, to the lead land pattern of the device. So then this leaves a pattern of solder paste containing flux for devices to be picked and placed on top of. And then this assembly is sent through reflow. So then afterwards, the process is the same. Devices are removed from the non-wetting ceramic substrate and inspected. The leads, the critical area of the leads, are inspected to see whether the solder reflowed properly. So this you would expect to be a much more accurate, much more reflective representation of true use of surface mount devices. However, despite that, this has not been as widely adopted in industry and is not as widely available from testing sites, perhaps because of the complexity of managing solder paste stencils for different types of packages and different outlines and different land patterns, and the cost of quality reflow equipment. So throughout this this process, throughout this industry, the importance of solderability throughout all the years of our industry, the standards governing this solderability testing have evolved and merged over time. So this JEDEC standard for solderability has progressed gradually from, as you can see in the chart on the screen, from more, shall I say, primitive versions of the testing to gradually becoming more and more advanced and becoming closer and closer to what occurs in industry. So for example, previously for reflow methodologies, there were only tin lead reflow profiles, the lower temperature profiles included. And eventually those were added to, and lead-free higher temperature reflow temperatures were incorporated as well to cover the shifts in our industry. And similarly, we can also see that the methodologies themselves have shifted throughout time. So the first methodology introduced was that dip and look method, which long predates the surface mount simulation method, and maybe from even dating back to the 70s when this type of technology and this type of mounting was more prevalent and more dominant. And since then, the surface mount simulation test method was introduced, but even that was quite some time ago. And so throughout this entire process, there have been little additions along the way that bring us closer to what happens in industry. And the latest rendition of that is the physical board mounting that was introduced in the latest revision of this JEDEC standard, IPC EIA JEDEC standard, which is that specifically physical device mounting on PCBs may be used instead of this simulation that we had previously prescribed using a ceramic substrate. So now we're talking PCB, devices directly on PCB, and that's what we believe may give the best results. So in order to probe that and to understand these different test methods and their applicability to different types of surface mount devices, we selected a variety of different types of product, combining various different types of surface mount packages, making sure to include the various types of leads that we would be most concerned with in terms of applicability of the surface mount test versus the old traditional dip and look test. And so specifically, we looked at the gull wing lead types, the very thin, narrow, fine-pitched leads found in, say, TSSOPs and quad flat packs that Dan had previously mentioned were, subject to possible obsolescence concerns due to trim-informed tooling, as well as other package types that do not require trim-informed tooling, such as the no lead, the QFNs or DFNs, as well as solder ball package types, so BGA. And specifically, we wanted to include a greater diversity of parts and part types and device package types than we had covered in our previous paper, to ensure that we cover as many types of lead counts as we can, as fine pitched as we can, to see the factors at play across all the different types of products that we're concerned with. And for this study, we were able to find some devices that were even older than the previous that we had examined. So the oldest device here, manufactured in 2002. So with this testing, we wanted to look at, one, which of those three tests, the dip and look testing, the surface mount reflow simulation, or the physical device mounting on PCB, would be most reflective of actual board performance. And two, we wanted to contribute this information to the literature and to the current understanding of the relevance of date code and whether date code restrictions are truly based in fact, so that this information can be out there for the industry. And three, of course, we also wanted to understand our own capabilities of whether we can develop this new process and deliver on it repeatably. So to do this, we performed this testing at two different independent testing providers, as well as at Rochester, the solderability testing. So we covered both dip and look, the oldest method, as well as the surface mount simulation. And then we also contracted board attach. So within the solderability test methods specifically, we use both types of preconditioning outlined in the JEDEC standard, which are steam preconditioning and bake preconditioning. The steam preconditioning involves exposure to steam for leads to simulate aging of leads prior to the beginning of the test, and the bake is meant to do the same thing. So both these methods were included, as well as both the types of testing, traditional solderability tests themselves, both the dip and look and the surface mount simulation. On the other hand, for the physical device mounting testing, that board attach process was performed at 3 different contract manufacturers, as well as at Rochester again. So for the Rochester testing, we used the identical reflow profile that we use normally in the simulation test, so that everything is kept consistent. And for both these types of testing, it's important to note that following the JEDEC standard, no pre-cleaning was implemented on devices. There was no surface abrasion or anything like that devices were used directly as removed from their packaging. And after this process, we used cross-sectioning and SEM to examine whether whether devices were well attached to the boards. And for the boards, these boards were custom designed to accommodate these devices using classic 4-layer FR4. So here are some of the examples of different types of results that we observed in our testing. So in our test results, we found that, in fact, there were some devices that did not pass the testing according to the standard and according to the standard's failure criteria. So what was surprising was that these rates, despite all these products being surface mount devices, were relatively consistent across both the dip and look test and the surface mount test, which is to say that the surface mount test did not show any meaningful difference between, there was no meaningful difference observed between the surface mount test and the dip and look test. However, it's also important to note that the results we observed were different across the two different types of tests. So if you look at the graphic on the screen on the right side, you'll see a comparison of representative examples of results from dip and look and surface mount testing for two different package types. So you can see in the QFN example that the exposed pad in the center was well covered by solder in the dip and look testing. But in the surface mount testing, that exposed pad was not fully wetted. And so this is a failure according to the J standard 002 criteria. On the other hand, for the SOIC package, the leaded package, you'll see that there are pockets of de-wetting or non-wetting in the dip and look test results. However, for the surface mount test, those leads were fully wetted and no such de-wetting was found. So it's a little unintuitive that, or perhaps surprising that we found these differences between the two tests that did not align. There was very little to no correlation between the results of the dip and look testing and the results of the surface mount solderability testing. And moreover, we also looked at the device age versus the results, as well as the package type and the results, and there were little correlations as well. So after looking at this traditional solderability test results, we looked at the PCB results. And so here is an optical image of representative part types of again, the three different types of board attachment methods, terminations that I had previously mentioned. QFN at the top left with solder pads underneath, BGA down below that with solder balls adhered to the board, as well as plastic quad flat pack to the right with gull wing shaped leads adhering to the board. And here again, you can see robust solder fillets externally. Now for a more detailed look, an in-depth look, these were also submitted to an external laboratory for cross-sectioning and SEM. So to see within the solder fillet to ensure that not only is it robust as we see externally, but also to probe within without needing to perform some kind of orthogonal or diagonal X-ray for the solder balls, which are not visible from the exterior, the internal solder balls. This cross-sectioning and SEM was performed. And so here you can see as well, similarly to the results of our previous study, the internal bond wires look good. The bond wires look well adhered to the die, and the solder ball fillets also, the solder fillets, I should say, both for the solder ball and for that TSSOP gull wing lead, all look good. and we found no evidence of non-wetting or delamination in any of the boards, and each of the contract manufacturers inspected the boards to the IPC A610 standard and found no defects. So to summarize the results of our testing, this gives us one summary graphic that represents the results across the different types of packages and across various bins of device ages that we used for testing, where we found rejectable criteria according to the traditional solderability testing across both dip and look or the surface mount simulation testing. So if either of those failed, we flag it here as red. And if none of the traditional solderability testing failed, all passes, no rejects found, then they're green. And you can see that there is a strong strong dissonance between those results and the board attach method, where the board attach method reflects what is done in industry. These contract manufacturers were reputable third-party contract manufacturers that we sought out for performing board attach according to their standard methodology with no additional instructions on special processing or anything of that sort. As they handle devices that they would normally have manufactured, this was the result. And so this incongruity between the traditional solderability test method and the new physical board mounting method is something that we wanted to highlight as a concern for specifically aged surface mount devices. And there are a few reasons that we may suspect for that. One may be, for example, that the fact that a preconditioning method is still required. That preconditioning method is meant to simulate device aging before product use. But in this case, that's for the JEDEC standard, which is produced under the assumption that devices are being tested as they're being manufactured, which is the case for Rochester's manufactured material. But for the case of devices that have been stored for a very long time and solderability testing is requested, well, what is necessarily the point of that aging process if devices have already seen a long duration of storage and naturally aged? So that could be one factor at play. And the board attach method eschews that preconditioning and simply reflects what is done at what would be done at the contract manufacturer's site. So we believe that this physical device mounting may be the most appropriate method and allow users of semiconductor devices, particularly aged surface mount devices, which is what Dan has been talking about, is going to garner more interest in the industry due to these market factors that Dan has discussed. For those products, it may be worth considering this type of board attach validation instead of a traditional solderability test screening, which may lead to over-rejection of devices that are, in fact, good devices with no reliability concerns. And that over-screening of devices which may already be difficult to source is something that we want to ensure that minimize waste in the industry. And with that, I'll pass it back to Dan.
Thank you, Neil. And I just want to emphasize that, again, all this product that we showed here was not cleaned, there wasn't any special processing to it. In fact, we didn't want to tell the contract manufacturers anything to do anything differently, just to see what the results were. And so, kind of wrapping this back up a little bit, and then some conclusions. So we're definitely in shape here, expanding our capabilities to do domestic manufacturing with billions of die under storage, enabling various packaging solutions to continue for those packages, several packages that are going away. And again, we have all this capability under one roof of design, assembly, test, and doing quality. The package styles that we are trying to put in place as these packages diminish in the industry kind of match what packages are going away. And you'll have this material afterward. I don't want to spend a lot of time on that. So again, the culmination of this multi-part study is really, we're putting this in place because lead frame assemblies that need trim and form are going away in the industry. Your plastic quads, certainly the through-hole stuff, and the PLCCs from the biggest assembly houses in the world, and that there's a couple that are well known. They're getting out of doing any kind of trim and form based assembly solutions. The volume's just simply too low. What that's going to do is it's going to drive people to do these last time buys and store product. And if it is all within the authorized channel, and that is everything we pulled out of our warehouse was fully authorized, never left the authorized channel, didn't go out to a customer and then we bought back any kind of overages. We don't do that. It is 100% within the authorized channel, AS 6496 compliant. That is all we deal in, is fully authorized products. So everything in this study was fully authorized, never left the authorized channel, was stored at Rochester in temperature, humidity controlled, double bagged sometimes, desiccant and so forth. That's how the product was pulled out of our warehouse, unopened, never left the authorized channel. So anyway, we think the industry needs to get away from unreasonable date code restrictions. You know, we've heard things from contract manufacturers especially, oh, we got to have 2-year date code. Why? Where's the data behind that restriction? We don't think that's a technical restriction. We think that's a business restriction, a business challenge that contract manufacturers have for long-term product storage. Absolutely, that's a problem. We acknowledge that. They've got a heck of a challenge on their hands. But from a technical perspective, we don't believe that long-term, fully authorized storage of products should have date code restrictions like 2 years and 3 years and 5 years. We're not seeing that makes any sense. The data says it's just not there for all the way up to 15 years. It doesn't make any sense. And that's not just us. There are other semiconductor companies, TI amongst them, who say, look, everything in our warehouse, they came out with a white paper that says 17 years. So we're in alignment with arguably one of the largest, certainly the largest portfolio semiconductor companies on the planet. They're saying, no. If the product is stored properly, if it's in a fully authorized situation, we don't see anything for 17 years. We're agreeing with them that date code restrictions of 2 years, 3 years just don't make any sense. And again, we're trying to help educate the industry. All this content's out there. The presentation material will be distributed, but we don't think there's any date code restriction that's reasonable here in the 2, 3, 5 year range. Again, purchasing from fully authorized distribution is the way to go. AS 6496. Anybody who buys excess brings it back. It has left the authorized channel. There's no guarantee of how things were stored, and they're bringing it back. That's not that. Again, stick with fully authorized the whole way. We've conducted this detailed analysis on solderability, mechanical integrity, electrical performance, stored up to 22 years. Again, we just don't see why there's date code restrictions that drop down. It's kind of an ancient history, we believe. We think the right way here is to jump back to the JEDEC standard there on the page here, in lieu of SMT or the dip and look method. So with that, I want to turn it back to Bill, and we start going through, hopefully get some of your questions. Quite a few questions have popped in.
Definitely. A few of you have already submitted questions, so we're going to jump right in. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. Okay, this one's a long one to start with. Why make this recommendation for device age and purchase from authorized distributors if not compatible between A-type, B-type, and S-type testing? Older date code parts may be from authorized distributors, but those distributors could have repurchased overstock they originally sold to OCM or system OCMs, and those components would still be considered authorized distributor sales to new customers, with the component being outside of their storage and handling procedures.
I'll take that, Neil. So, what the scenario that was described there with that really long question is actually not an AS6496 storage environment. AS6496 says the part never left the authorized channel. That means it didn't go out, it didn't get resold, it never left the authorized channel. When you stay fully within the authorized channel, that means your largest distributors, for example, of Arrow and Avnet, they're really large distributors. Those are 100% within, provided you don't drop down to some of the broker arms. If you're really staying within the authorized channel, you're not leaving, you're not going out, you're not coming back. That's the distinction we're making. If you're, what TI's white paper went through was products stored at TI. What our white paper and presentation here has gone through is products stored at Rochester. Both of those examples are AS6496 compliant, never left the authorized channel, always stayed within the authorized channel. There's no resale, going on back and forth. They're not brokering parts. When you have brokered parts, unless you can audit the entire channel, the entire path that those parts took, you're not going to be assured that all this data we're providing is accurate anymore, because now you don't know about storage. And so we still think the 2-year date code thing, even with all that, the 2-year date code thing is going to be over restrictive. And I welcome anybody who's got data, real data, that says, hey, I've got these parts, they're 2-year date code and things aren't working, they're not soldering onto the board. I welcome seeing that data. We've never seen that data. So again, I challenge the audience there, provide some data coming back, because we haven't seen it. That'd be great to see.
Okay.
To provide clarity for the audience, the A-type, B-type, S-type that this question referenced, the A refers to that dip and look type, the B refers to dip and look specifically for leadless packages, and the S-type refers to the surface mount simulation type of testing that we described. And the physical device mounting is a new sort of subset within the S-type testing.
Okay.
Thanks, Neil.
When you do this testing on BGA, do you have to reball the BGA parts?
Go ahead, Neil.
Great question. I'll take that one. So, in fact, the BGA parts cannot be dip and look tested, because, as you allude to here, the solder balls would just melt in the solder pot. So, the only type of testing that was performed on the BGA was the surface mount simulation type of test, as well as the physical device mounting. And because the solderability testing is considered to be destructive, we don't reball or reprocess these for then use or sale. These parts are considered scrap after they've been used for testing.
Okay. How do I identify with Rochester or distributors or TI and OCM that component purchase is within AS6496 control?
Okay. You can ask for traceability on the product. That certainly is an option for you. Although if you're buying direct from TI, you have to assume that it has never left TI. For Rochester, who is an aggregator of all things authorized from everyone, that it is a traceability request, and that isn't necessarily a free option, depending on how old the product is. But that is something that we're routinely requested, is to provide that traceability path that gets you back to the original manufacturer and making sure that it always stayed within the authorized channel.
What were the sample sizes of the various component packages used to determine solderability?
Good question. So we followed the J standard 002 standard sample sizes, and those outlined in JASD 47, the standard for package qualification for plastic packages and commercial applications. So 3 devices, 22 leads, detailed, inspected, and 100% as well looked at. And this was replicated across each of the different test sites. So for traditional solderability testing, that was 3 different sites, 2 external and 1 Rochester. And for the board mounting, that was all boards were inspected across the 3 contract manufacturer sites as well as at Rochester.
Okay. Could you please address the differences in flux activity used? In particular, test flux versus production flux is a major issue.
Right. So my understanding of this is that test flux is may not match the activity of production fluxes, which may be more aggressive, in fact, in removing oxidation and those types of flux activities. The flux used by Rochester Electronics in the board mounting process was standard test flux that we use for our included in the solder paste that we use for our surface mount simulation solderability testing. So no different from that which is outlined by J standard 002 and J standard 003. And for the contract manufacturers, we did not specify. As Dan was saying previously, we don't want them to change anything about their standard process to ensure that this testing is as relevant as possible to industry concerns.
All right. For, quote, traditional solderability methods, did you include any samples without preconditioning, such as no steam and no dry age?
No, not for this study. This study did not include any omission of preconditioning, because we wanted to ensure that everything we cover within this study was fully compliant to the JEDEC standard. And whereas you may have an agreement between the user and supplier that preconditioning is optional for this application, we wanted to focus on specifically more scenarios that are applicable to everybody without needing a special stipulation that, okay, we've agreed that preconditioning can be omitted.
Okay. Is there any indication as to the farthest extent to which parts can be stored before seeing degraded solderability? It seems that the comfort level is still growing from the 2 years to the 15 to 20 years. Is there any indication of how far it may go?
Well, I'll take part of that, and then Neil, I'll let you jump in. TI was 17 years, but that's only because their study just limited it that they didn't have older ones that they grabbed at the time. Ours went out to 22 years. I think it all comes down to ensuring that the product, again, never left the authorized channel, wasn't sold to an end customer, if you need another definition there, wasn't sold to an end customer who then decided they didn't want it anymore. That's leaving the authorized channel. We're seeing that a reasonable date code to come into some concerns is for us, it'd be all the way out to about 15 years before we start having any concerns about our product. And that's only because we simply don't have the data beyond 15. Look, we're trying to move people from 2 and 3 year date code out in time. So we expect to walk before we run. But right now, if a customer came to us and said, hey, anything older than 15, we want some more analysis done, we want some more checking done, that would be very defensible. We don't have data to back it up, but under 15, we just don't see it when it's been properly stored.
Right, and also to address what the person asking this question may be thinking of, we don't see any kind of clear cutoff. There's no indication that there's any kind of date at which suddenly devices go from passing the traditional solderability tests to not passing the traditional solderability tests. So there's not any kind of date that we could recommend that is appropriate, which is why we stress that a more applicable, a more realistic testing method or screening method is really what will give you the best indication. And again, we think that that could extend as far as we've studied, which the oldest device goes out to 22 years. But again, the data in the upper range of that is we have fewer devices to pull from. And others, of course, have even less research done on the older date codes.
All right. Is there a correlation in percent between the acceptable wetting results of reflow simulation method and real board level processing?
No, we didn't see any correlation because we weren't able to find any defects in board level processing, right? So regardless of what results were observed, either in the wettability at using the surface mount simulation test method or the dip and look method, we saw no real reflection of that in terms of true device mounting to PCB.
How does the obsolescence of certain package types lead to more long-term stored components?
Yeah, that question is as a result of the long-term market demands and the accelerated obsolescence of packages that need trim and form tooling. So if you kind of look at automotive is a good example, and of course commercial avionics and mill. But if you look at their demand for any products that have packages that require trim and form tooling, we're seeing this wave of obsolescence happening on those types of packages. We think a viable solution to that, part of the toolbox of solutions, is storing product long term, and certainly longer than what previous date code restriction kind of mentality would let people do. So part of I guess a portfolio of solutions that we would propose to a customer is going to be a mix of building and storing along with investing in assembly solutions that we're doing at Rochester to perpetuate a product availability. But we think there's a strong correlation and a demand now that's going to happen for products that require trim and form tooling to need to be stored. That the last time buy is going to happen and people are going to want to store that product. And we think as long as it is stored within the fully authorized channel and pushed out of that, stored correctly, you're going to get some nice long life out of that without having to do this over rejection based on 2-year date code and solderability testing that isn't proving to be correlating to reality.
How would Rochester Electronics recommend discussing the removal or reduction of date code restrictions with management?
Well, it kind of depends on where it's coming from, but honestly, if it's coming from a contract manufacturer, it might be getting pushed to them from their OEM customer, in which case there's got to be this pushing of real data, and we're providing that to you backwards to the OEM who's driving that and the contract manufacturer to be the case. We want to help educate those that there really isn't that correlation to date code, especially in the 2-year, 3-year, 5-year time frame. There's no data that says that that's a problem at all. And so I think it's more of an education process. I think it's let us help you work that education process backwards into whoever's driving it with real data that says, no, there really isn't anything that says there's a concern here.
For those who follow date code restrictions because of customer requirements, what can be done to educate the customer about current date code understanding?
I think there's a couple things. One is all the material that we've got out there, and two is probably bringing somebody like my friend Neil here in to talk to them a little bit more about what we did and how we did it. But it's also referencing more other industry papers that are out there too. There's the TI paper that they've kind of revised several times over the years, and there's one from Allegro as well. There are other people who are saying this. ECIA came out with a statement that is really the 2 to 3 year date code thing is without any data to back it up. So I think it's more getting people to get off of that as a statement without having fact to back it up, and more providing facts that we've seen, that we've actually spent the money and the time and the study effort to prove, no, it's really not an issue. I think it's more just an education process. I think 2 year date code is something that came from 30, 40 years ago, where it might have made more sense with the assembly types that were in place then, the materials that were in place then, and the manufacturing methods that were in place then. I think that all might have made more sense than it does now.
Well, I'm afraid we've run out of time. For those questions we didn't have time to answer, we'll be getting back to you via email. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank our sponsors for their presentation today. Rochester Electronics for sponsoring today's webinar, and of course to all of you for joining us. Have a great rest of the day.